Good morning. Today, I'd like to look into some consequences of our recent discussion. In the situation where we have a weak gravitational field and objects move slowly, we discovered that G00 should be approximately -1 plus 2 times the gravitational potential. If I put in the inverse distance potential into that thought, I find out that G00 should approximately be the negative of 1 minus 2gm over r. We're going to adopt a toy problem in which we describe the 0, component of the metric in the way that we've decided. For the case of a point particle, the coordinates I'm going to use will be x0 is time, x1 is the radial coordinate in spherical coordinates, x2 is theta, and x3 is phi. Looking at that metric, no component of the metric depends on time, that is x0. This means u sub 0 is a constant of the motion, and we all know how we raise and lower vector and tensor indexes now. This is equal to g0 beta u beta. Since g is diagonal, this means that this is going to give me a relatively simple formula for u sub 0 along a geodesic. I can give this constant any reasonable name. Of course, it shouldn't involve the letters G, M, R, T, or tau, and probably not D either. I'm going to call this value, which is a constant, the negative of E. Along a geodesic, dt d tau will then equal E divided by 1 minus 2gm over r. A word or two about the meaning of this E is probably in order. Suppose that r is extremely large, so that the denominator is practically equal to 1. This says then that dt d tau is approximately equal to this constant, E, but from special relativity, we know something about dt d tau. Far away from r equals 0, E is going to be 1 over radical 1 minus v squared, where v is the speed of the individual whose proper time we are examining. If you are both very far from r equals 0 and moving very slowly, then E will approximately be 1. If E differs significantly from being 1, it's either because r is not very big, or v is very big, or both. In a similar way, no metric tensor components depends on theta, x number 2, therefore p sub 2 is a constant along the geodesic, u2 is a constant along the geodesic. In a way similar to before, this tells me that r squared sine phi times d theta d tau must be a constant. In a moment, I'm going to look for geodesics that lie in the plane, that should be in quote marks, where phi is pi over 2. If this actually were special relativity, that would be the xy plane. It's worth mentioning that there might not be any such geodesics, but if that's the case, we'll find out when we try to solve the differential equations. This gives us back our familiar conservation of angular momentum formula. I'm going to form the dot product of the 4 momentum with itself. This is a dot product of two 4 vectors. I'm going to just write it out using the components of the 4 momentum and the metric tensor. On the other hand, at any point that I wanted to look at this, I could establish a local Minkowski coordinate system at the location of interest, use those coordinates to do the dot product, and I would have to come up with the negative of the mass squared. Since m squared shows up as a factor in each term on the right and also as a factor on the left, I can divide the little m squared out and it disappears completely from the problem as it should. However, we know something about dt d tau and also something about d theta d tau because of that constant along the geodesic business. This is beginning to look remarkably like the calculations done in the polar express problem and also in the video, What Would Isaac Newton Do? Just as before, introduce a new variable, u, then express dr d tau in terms of u, and then use the chain rule to convert du d tau into du d theta d tau. From our constant along a geodesic thing, though, we know that d theta d tau is h over r squared, that is to say h times u squared. The derivative of r with respect to tau is the negative of h times du d theta. Aside from expressing this term in terms of u, we are in a position that's very similar to what Isaac Newton would do. At this stage, I'm going to differentiate both sides with respect to theta, just as we've done in the past. I'll divide out 2 h squared and du d theta. In the toy model, the differential equation for the orbit of a planet is going to be second derivative of u with respect to theta plus u is gm over h squared e squared times 1 over 1 minus 2 gmu quantity squared. If r is big, u is small, and this fraction at the end is approximately 1. If not only r is big, but the speeds are small as well, we figured out that the e would approximately be 1. So in the case of far away from the source of gravitation and not moving too quickly, the geodesic equations that we have figured out reduce down into the same formula that we got in What Would Isaac Newton Do? To a first degree of approximation, our new way of thinking, particles are moving in the straightest possible paths through spacetime. That idea has reduced down into the circle, ellipse, parabola, hyperbola situation. It's worth mentioning, though, this model can't be right. This can't be the correct metric because we already know from special relativity that space and time are linked together. I can't have a modification of time without having some modification of space as well. But even so, even at this relatively early stage of the game, we can see that this can work for us. I can get Newtonian gravity out of this follow the straightest path through space-time business. I hope everybody's having a good day, and I'll talk to you again soon.